a little bit longer with rates of change, and in particular I want to focus on moving object questions essentially. We've done quite a lot of these types of questions, but there are some bits and pieces I want to dwell on just a little bit longer. So here is the position of a curve at a given point in time. And I'm going to go through some of the things that you could be asked about this moving object. Pretty straightforward to start with. You might get a question where they ask you for its velocity. And we know that's the first derivative, right? A rate of change. So the rate of change of position with time gets you velocity. Right? Rates of change are derivatives. So in this case, it's basically a whole load of power rules. And then you might be asked, well, what was the velocity at the 2-second mark? Well, you just go 4 lots of 2 cubed, take away 12 lots of 2 squared, take away 16 lots of 2, add 15. I am not going to even try and do that in my head. Let's see what you get then. That's 8. So you're going to go 4 times 8, take away 48, take away 32, and finish with add 15. And the answer, put it down here, I think, is negative 33. So there are probably going to be some units. The most common units are some unit of distance per unit of time. So it could be meters per second, miles per hour, feet per minute, whatever it is, right? Whatever sign typically tells you that. So there's velocity, nothing too surprising about that. You then might be given what is the acceleration. Well, the acceleration is the double derivative of the position, or you can think of it as being the first derivative of the velocity, because the rate of change of velocity with time is the definition of what acceleration is. So let's see what we get for acceleration. You differentiate that guy. You differentiate that guy. You differentiate that guy. And there you are. And you might get a similar question, which is, what is the acceleration at the 2-second mark? And it'd be 12 lots of that. Take away 24, take away 16. Do that. Oh, wait a minute. 48. 48. Oh, negative 16. Not sure I could do that one in my head. And the units for acceleration would be distance per time unit squared. So meters per second squared. Then you might get a question like, is the object speeding up or slowing down at the 2-second mark? Well, we talked about this yesterday. The velocity is negative 33 meters per second, right? So it's going downwards at 33 meters per second, I guess. Or if you want to call going to the right positive, then going to the left would be negative. So it's got a velocity of that, and it has an acceleration, in this case, of negative 16 meters per second. Is an object slowing down or speeding up when both its velocity and its acceleration are negative? What's it doing?
Speeding up.
It's speeding up. And we talked about that yesterday, but just to remind you, if they're both the same, That means if both of them are positive, it's speeding up. Or if both of them are, in this case, negative, it's speeding up. If it's one of each, it's slowing down. So by only being given that one piece of starting information, which is essentially telling you where it is at any given time, we can find velocities at any given time. We can find acceleration at any given time. We can tell you if it's speeding up or slowing down at any given point in time. Right? So there's a lot you can do with that. But we're still going to do some more. You can also be asked questions like, you can also be asked questions like, when is something going to happen? So here's two examples of that. First question might look like this. When is the velocity, oh, I don't know, minus 10 meters per second, right? And what would that be? Question D. When is the velocity negative 10 meters per second? You could also get, when is the object stationary? Well, let's have a look at that. If you want to know when the velocity is negative 10, what you would do here is, wouldn't you solve this equation? Right? When is that negative 10? And our velocity is this fella. Now, unless this is a very simple quadratic, you really wouldn't want to try and solve that algebraically. I'm not even sure it's possible. And it could easily be that the answer isn't even a whole number, right? It could be 8.12345. So you're probably going to have to round off the answer, let's say, to 2 decimal places. So whenever we come across a horrible equation like this one, shouldn't we think about Desmos? Right. So let me kick over to Desmos and look at solving that problem. So we're going to put in v for velocity is equal to 4t cubed. Oops. 4t cubed, that's good. Take away 12 p squared. Take away 16t. And then add 15. And then I will just put velocity equals negative 10. And it'd be a fluke if I got a decent window. And as you can see, I didn't. Why is that not showing up as negative 10?
Professor, we can't see Desmos.
You can't. Thank you for telling me that. I thought I'd switched over, but I haven't. Right, there we go. So there is this guy. I'm trying to do negative 10 here, and it should have went negative 10. So I'm going to go for plan B and just call it Y. And let's see if it handles that then. There you go. Okay. Evidently, it needs to be Y equals. So pretend that Y represents velocity, which it does. Now, do you see down here, the blue line is meeting up with the red line. Now, the scale is ugly and you can't really see everything you want to. So I'm going to change some windows around. And I'm going to assume that time starts at 0. Which
Also, the 15 wasn't in the first derivative. That was the original function.
Oh. No, 15 is in the derivative. There was a 15t in the original and then a plus 15 in the derivative. It's worth telling me that because I do make mistakes. So I don't
My
have a problem
apologies.
with it. No, I'd rather you tell me and I was wrong and let it slide. Okay, so I'm going to shrink this back a bit. Okay, there. That'll have to do. If you notice that the blue and the red lines cross at two places, so I'm going to click on that one, and then I'm going to click on that one. So to, let's say, 3 decimal places, then won't the solution be at 1.036? And the other one would be what, at 3.628? Are you comfortable about just plug in the velocity, plug in what velocity is equal to? Just remember to call things y, and they will cross over, and they'll intersect, and you just click on them, and Desmos is pretty good at telling you the x and the y values of the points. We cool with that? Right. Now, the second question, since I've got Desmos in front of me here, right, was when is the object stationary? So they didn't mention any numbers, but they said, when is the object stationary? What velocity are we talking about when they say that? What is the velocity of an object that's stationary?
0.
Right. So aren't we basically trying to solve when is that velocity time thing equal to 0? And from what I can see, it's a decimal as well, won't it be? There we go, roughly about that number. And it's going to happen twice, so there's the other one. So for that, the solution would be at 0.674 seconds. And the other one would be at 3.794. And let me return now to the big screen. There we go. Right, so if you want to find when the velocity is -10, don't we use Desmos? And here are the two solutions that we got. If you want to know when it's stationary, don't you solve when is the velocity 0? And Desmos gives me those two guys as well. Now, if the answers are nice whole numbers, that's fine. Desmos will tell you it's 1. And if it's not, it'll tell you it's 1.036, as it did here. Are we good? Right. Now, in a similar vein, so this is really only for completeness sake, you could also get things like when is a acceleration equal to, I don't know, -4. And you could get when is the acceleration 0, right? Well, if you wanted to do that, aren't you going to work with the acceleration function? So for the first one, you would solve when is acceleration equal to -4, which becomes 12t squared take away 24t minus 16 equals -4. And if you want to know when it's stationary, you would solve when it's acceleration. I said station, I mean 0. You would solve this fellow. Now, these are quadratics, so I could probably have a shot at trying to solve this by factoring, and it might work, and that'd be great if it did. But it might be, I need a quadratic formula, or it might be I'm going to use Desmos. I'm putting you in a spot, William. Do you want to factor it? Do you want to use the quadratic formula, or do you want to use Desmos?
I would rather use Desmos.
I would rather use Desmos. Would that be the general opinion of everyone here? Right? It just takes a lot of the strain off the process. So you're going to have to kind of bear with me for a second while I just doctor this one so it looks like the acceleration function. So it's going to be 12t squared, take away 24t, and then it's what, minus 16, And then the question I said is, when is it -4? Which is that one. And technically speaking, there's an answer over there, but since that's a negative time, we're ignoring it. Time typically is only in positive direction. So there's the answer, 2.414. And if you want to know when it's 0, would you agree it's that point there, which is what, 2.528. I've written those two down. And we are pretty much done everything I think you could do, with one exception, to a position function. Would you agree that calculus gets you a lot of stuff? You start off with just knowing where it is, and calculus tells you a lot more about that moving object. It tells you its velocity, its acceleration. You can solve equations and find out when it's slowing down and speeding up, when it's going a certain velocity, when it's stationary, when its acceleration is a particular number, when its acceleration is 0, and so on. So what is the only situation that I haven't covered? And it sounds like it's the easiest one, and it's actually the hardest. We are going to look at, how do you find the distance traveled by a moving object? Now you might think, oh, that's easy. Well, it's not. I have a question set up. Okay. Imagine I give you the position of an object, and it's this fella here. And I would like to know the distance traveled in the first 6 seconds of that moving object. Now you might think, oh, I just find out where it is at the 6-second mark, and I find out where it was at the beginning, and whatever that is, take that away, and that must be the distance traveled. That does not work, but let's go through it and show you what number you get. So I have 6 cubed, take away 9 times 6 squared, plus 24 times 6, and the answer I get here is 36, and the answer I get here is 0. And so you might assume that this object has traveled a distance of 36, let's say the units are meters, in that 6-minute period, right? And the logic would be, well, it started off at 0, and 6 seconds later, it ended up being 36 meters away from where it started. And so it must have traveled 36 meters. The reality is that that object has traveled more than 36 meters. And you might think, well, how does that work? How can that be possible? I want you to imagine that I draw a sketch of a different function, right? A different position function. And this position function, at time 0, you start off at your house and you just walk, I don't know, 10 meters, and it took you 5 seconds. And then you walked all the way back home because you forgot your keys. That's 10 seconds. And then you walked 5 more seconds. You should always plan ahead when I do these things. And you ended up here. Now, if I went and said to you, how many meters did you travel in that journey, right? That 15 seconds. Well, 5, that's 10 meters, right? 10 meters home, 10 meters back again. Wouldn't that be a distance of 15 meters I walked? Because distance does not have a plus or a minus. Isn't distance a positive thing, right? I only can walk positive numbers, right? It's not like velocity or acceleration. If you want to know the jargon, distance is a scalar, right? It's not a vector. So that is 10 there, 10 back, 10 more. That should have been 30. The position of this object at time 0 was 0. The position of this object 15 seconds later is 10. Do you notice that if you subtract those, you will get the wrong answer for how far you have walked? Do you see it doesn't work? You cannot use position at start, position at the end, and think if you subtract those two, that is the distance that you have traveled. You might say it's how far away from my front door am I? That would be correct. I am 10 meters away from my front door, but that's not the question that was being asked. The question was being asked, I'm walking with my feet. How many feet did I travel, or how many meters did I travel? So that's the puzzle. How do we come up with the answer to the distance traveled when it does depend on what the shape does, right? What the position curve is doing. So the answer is a lot nicer than you think it's going to be. Now that we've got this thing kind of sorted out, is that you can use Desmos. Now, I'm not sure where the heck are you looking at a Desmos picture of t cubed minus 9t squared plus 24t? Are you looking at that guy? Right, so our question is, what's the distance you traveled in the first 6 seconds, right? That's what the question was. It's one of the homework questions, right? What was the distance traveled in the first 6 seconds? Now, what you do here is you identify zero derivatives. So you see at that point there's a zero derivative. So, and then at this point here, there's a zero derivative, and that one up there is just the end of the journey. So I've just told you that that one happens to be 36. You can check it out. So if you want to know the total distance traveled, you go like this. Starting off at 0 to the 2-second mark, you see I've traveled 20 meters. So you write that down, 20 meters. That's, I'll call that A, right? So from there to there is A. That's 20 meters. Now, from the 2-second mark to this point where the derivative is 0, right? It's basically when the thing turns, right? From here, 20, to here, 16, doesn't that indicate 4 meters, right? Start to finish, there's a difference of 4. And I don't care that it's positive or negative, because it's always going to be positive because it's a distance. So I went 20 meters in the first 2 seconds. From the 2-second mark to the 4-second mark, I've only traveled, what, 4 meters? And then right at the end, from 4 meters to that guy there, who happens to be 6,36, right? So from 4 seconds to 6 seconds, it's from 16, and you finish at 36. So that is another 20 meters. So basically, break your shape into 1 piece, 2 pieces, 3 pieces, and your shape will be split at the points where hills and valleys are, right? Zero derivatives. And then you take all 3 pieces of that journey and add them up. So 20, then it was 4 for the little bit, and then it was 20 at the end. And that gets you the 44 meters that you've traveled. Do you want to see another one of them? Or are you comfortable with the process? We're comfortable with that? Okay. You're comfortable? I'm happy. And that's pretty much everything that we want to know about a moving object right now. Right? We've got the whole start to finish. You can tell anything, you know, within reason, what that an object is doing. I think that is that one done. Yes. Just checking that I haven't missed anything. Just going through the homework questions. Oh, we have, yes, but that's not a velocity question. Okay. The next question is a velocity question, or at least a moving object question. And the only reason I want to spend some time on this is because it's a trig function, and trig functions tend to cause problems. So this is a version of question 11. And they call them f of t, but I prefer s of t. And we have a moving object that looks like that. The kind of objects that move like that are springs. You know the spring where it bounces up and down, side to side, or if it's a suspension, you know, the spring moves up and down vertically. That's what suspension does, right? It absorbs some of the movement, makes your journey a little bit nicer. So in a question like this, you're going to be asked velocity. You're going to be asked find the velocity at a given number. So let's go through those ones. If you're going to differentiate this function, I hope you recognize that it's a general. And it's going to be the cosine of this inside function times the derivative of this. Now, if it helps your brain, couldn't I write that guy like that? Does it make it a little bit easier that its derivative is pi upon 2? We cool with it? Right. So the velocity of this moving object is pi upon 2 times the cosine of that guy. So if you're being asked to find the velocity at the 1 second mark, you would be calculating that guy. And hopefully you all know that the cosine of pi upon 2 is 0. So the velocity of this object would be 0, which makes sense. Can you imagine that a spring is, you know, getting crushed and then it gets bigger and then it crushed, right? So it's bouncing up and down. But isn't there an instantaneous point in time where it stops moving, right? From going up to going down, there's an instant in time where it's stationary, right? That's essentially what you found happens at the 1 second mark. Now, suppose you're being asked to find the values of t when the object is moving in a positive direction. So what you're trying to do here is you're trying to solve when is the velocity a positive number, right? So for what values of t? How do you think we're going to solve this equation? How are we going to solve that? No takers yet?
Find the derivative for a 0 slope, and then because that's the point of change, a positive slope would be increasing, and that should be where velocity is greater than 0.
Oh, that is totally correct. But it's not the way I'm going to do it. But it would work, and there's nothing wrong with it. And go ahead and do it, because it is a nice way of looking at that. You can't see what I'm doing right now, but I'll show you in a few seconds. I'm doing Desmos. Here we go. Right, so what I was doing while I was talking there is I was setting up Desmos with our derivative guy. Okay. Now, when you see Desmos, we'll start at time 0. Isn't the velocity positive from here to here? And then from here to here, and from here to here, essentially forever, isn't it? Right? So just looking at the graph then, I should be able to come up with what they're looking for. Well, it's going to be from 0 to 1, and then it's going to be from 3 to 4, and then it's going to be 5 to 6, and I guess that's forever. So now I better read the question and find out if they had a kind of restriction. Otherwise, I'll be writing for a very long time. And they only want to know the first 6 seconds. So I'd stop. Right, I stop there, right? Okay, first 6 seconds. Positive, positive, positive. Okay. It then goes on and asks to find acceleration, which I'm not going to do, and then find acceleration at 1, and then it asks you to draw them all and, you know, put them all together in one graph and pick from a set of 4. So that's kind of that question over with, at least as much as I wanted to do. Next one I want to do is do a speeding up, slowing down. And I want to do in a fixed interval. When is it speeding up? When is it slowing down? Right. So I want to do another one of those guys. So I'm gonna have to do a little bit jiggery pokery. If we can hang on there for a few moments. Not bad now. All I'm doing right now is creating a question that is going to work. Yeah, that'll do. So suppose we have a position function that looks like this. And I want to know when is it speeding up and when is it slowing down. And we're only interested in the first 10 seconds. Okay. Well, the way that we will do it is we will find the velocity function. And then we'll solve when is it 0. So I'm going to pull out 4t squared as a common factor. Okay, I'm going to move that to 20 so it fits. And so it's at t equals 0 and at t equals 12, the velocity is 0. Okay? So find when the velocity is 0. Then get the acceleration. Pull out 12t as a common factor. And you will get what? T equals 0 and t equals 6. So if you ever get a question of here is the position of a moving object at a given time t, within a certain interval, let's say 0 to 20, whatever it might be, tell me for what values of time it's speeding up and for what values of time is it slowing down. You will find the velocity and make it 0. You will find the acceleration and you will make it 0. And now you're going to make a very interesting little table. You're going to do a velocity table. And underneath it, an acceleration. And right at the top, you're going to have time. Time starts at 0. And you're going to pick little snapshots of time. 0, gotcha. 6 seconds, gotcha. 12 seconds. And in this one, you finish with 20. These are critical numbers. These are special values of time where either the velocity is 0 and or the acceleration is 0, or it's a start or finish of the time interval. And as you can see, there's lots of overlaps. Right? Now, for these key numbers, we are going to find the value of the velocity and the value of the acceleration. And I don't care what the number is. I only care, is it plus, minus, or 0, right? That's the only things that matter. So here is our velocity function, which I'll just write underneath here. It's t to the 4, that guy, plus 5, right? At time 0, the velocity is plus 5, but all you write down is plus.
That's the position function, sir.
Oh, thank you. At time 0, this is 0. Okay. And what's acceleration? It's also 0. Move on to the 6-second mark. I better write down the acceleration. The correct velocity, it's my scanning that's causing trouble, is that guy. And the acceleration function is that guy. I'm writing down the style point versions. Okay. At the 6-second mark, would you agree that this is 0, right? And what's this going to be at the 6-second mark? That's negative. That's going to be negative. Okay. At the 12-second mark, this is going to be 0. And acceleration is going to be positive. And at the 20-second mark, this is going to be positive. And so is this going to be positive. Okay. So what we're now going to do, I wish I'd left more room. I wasn't planning as well as I could have. I'm going to choose a point somewhere between 0 and 6, between 6 and 12. Really, I don't need that one because it's an endpoint for completing the sake, I'll put it in. So I'm going to pick a point like 3, 9, and 15. And now I'm going to take a little snapshot of what's going on there. The velocity at the 3-second mark is negative. The velocity, the acceleration at the 3-second mark is negative. Here at 9, is it looking at 9? Still negative. 9 is positive. And 15, everybody is positive, everybody is positive. Right. Now, velocity, acceleration. There's 0, there's 3, there's 6, there's 9, there's 12, there's 15, and finally, here is 20. So these little number lines, I'm getting the data from this table. So here goes. the velocity is 0, so is acceleration. At the 6-second mark, this guy is negative, and this guy here is 0. At the 3-second mark, everybody is negative. At the 9 seconds, you have a negative and a plus. At 12 seconds, you got a 0 and a little plus. At the 15 seconds and at the 20 seconds, you've got a plus. Now, once you've got these, which is basically, you could have done it with that table, but I'm just doing this because it looks nicer for me. Find any guy that's got a 0 and do a little dotted line through. Don't matter if it's a velocity, doesn't matter if it's an acceleration. The zeros are the places where things will change. So let's look at what's happening in, well, technically I should have one over here as well. Right. So what's happening between 0 and 6 seconds? Well, in that range, the velocity will be negative all the time, and the acceleration is negative all the time. So if they're both negative, it's speeding up. In the 6 to 12 second mark, isn't the velocity negative and the acceleration is positive? Now, what do you know is happening when those two things are going on? Speeding up or slowing down?
Slowing down.
Slowing down. When we say plus and plus, it's another speeding up. So the question was, when is this thing speeding up and when is it slowing down? Well, I can look at this and I can now say it's going to be speeding up from 0 to 6 seconds and then from 12 to 20. It's going to be slowing down and that's going to be from 6 to 12. So the key to doing this type of question is find out when the velocity is 0, find out when the acceleration is 0, and then pick some test points in between those. Make a guy that looks like this. Break the thing into pieces using when either one of them is 0, and it doesn't matter which one. Those are the separation points. Anything between that then is your intervals. And there's going to be a changeover typically from a speeding up to a slowing down, or from a slowing down to speeding up again. Are you okay with that method? You want to see another one? Are we good? Okay, good gets it. For completeness sake, there's a question at the end, which I just noticed. Probably I should have put it earlier on, but and this is for those who are business majors, an application of calculus in a business model. This one is a function that is called the, what is it called? Yeah, it's a cost function, although they don't call it that, that's what I would call it. And 0.0002 x cubed. So if you wanted to know what's going to be the cost of this company producing 1,000 shoes, X would be 1,000, you plug it in here, and that would be the total cost of producing 1,000 shoes. If you're into business, do you notice that number is 2,000? Isn't that the fixed cost? If you're in business, you have to pay people even if they don't make shoes, right? I'm assuming you've hired some people. Don't you have to pay rent for the building if you're renting it and all the other things? So that's a fixed cost. I would assume that if you are running a reasonable business, that when you produce more shoes, doesn't it, its unit cost goes down. What that means is that if you make 1 million cars, isn't the cost of each car less than if you only produce 100 cars? You know, you have mass production, all that kind of thing. So they have a thing called marginal cost. And the marginal cost is the derivative. So don't you just differentiate that horrible thing and get an equally horrible answer? It'll just be a equally horrible quadratic. And then you might be asked to find the marginal cost at 100. And what that is telling you is the rate of change of cost at the 100 shoe mark. So when you calculate that number, I'm just going to pretend I know what the answer is. Let's pretend it's $50. What that is telling you is that the 101th shoe will cost you $50 to make. Okay, so you can use marginal cost, which is basically the derivative of the cost function, to give you a little snapshot of where things going. So, not being a business person, but imagine you're only going to do a limited run of 100 Nike shoes, right? Green and yellow stripes with Seahawks on it, some stupid thing like that. You know, there's at least 100 idiots in the world that are going to pay money for those shoes, only because there's only 100 pair of them. No matter how ugly they are, don't matter. I have a nephew who, just share it, he never bought anything unless it was, you know, it had a brand name to it, right? So he could get a perfectly good t-shirt for £10, but he would spend £100 because it was some fancy company. Total idiot, in my opinion. That's what these guys are for, aren't they? Right? Aren't there idiots in the world right now that'll pay $500 for a pair of Nike special edition shoes? I hope I haven't insulted someone who's saying, oh God, I'm one of those people, I did that once. Right, okay. But that's it. So, moral of the story is, if somebody gives you a function and you don't know what the heck it's about, and then they ask you to find something else using that function, your go-to will be to differentiate it, right? So if somebody says, here's the charge function, tell me the voltage, you're going to say, I know what a charge is, I've never even done physics. Aren't you going to differentiate the charge function to get the voltage? Because that's the only guy in town. Right. So for those who are non-scientists, it don't matter what they tell you the thing is about. If you differentiate it, that will be what you should, I'm guarantee that's what you're going to have to do. So we are now finished that section, and we're going to continue to the next one, which is not a mistake. It's going to be 3.9. So you might think, what happened to 3.8? We don't do 3.8. It's not in the course, never has been. There are certain functions that we really are either not interested in or don't have time to cover. And one of those functions is the hyperbolic sine, cosine, and tan functions. So we skip that section. And one of them is, I just put 3.8 down, didn't I? And one of them is the exponential function. And we just don't do the exponential because it takes too much time and it's not that big a deal. Anyway, you could do it if you wanted to. So what's related rates going to be? Well, related rates are expressions or formulas where all the variables which are typically things like x and y and r, etc., where all the variables are functions of time. And I'm going to pause for a second, because this young lady, come here, gotcha. This young lady, Chloe, has just, I've noticed, chewed up her bed because I've been ignoring her. So we've now got a big load of fluffy, was it kind of brown coloured settings. And she knows she's in trouble. Can you tell looking at her face that she knows she's in trouble? Yes, you young lady. You're going to go and see your mum now. Okay. That is about the second bed that she's chewed up since we've had her. And she's only, what, 7 months old. God, she's a expensive little girl.
My dog's done that a bunch. They make indestructible dog beds that are really hard to break through and chew up, and that's worked for us.
Where did you get it, Carl? From being nosy, can you remember? If you can't,
Um,
send me an email sometime when you find out.
Another
Okay.
email. Probably Kong. That Kong makes one. They're at PetSmart.
I will look out for them. We need something. You need to have indestructible shoes, because she's already chewed 2 of my sandals, and I think she's into the 3rd pair of my wife's slippers. So we have a chewer on our hands. Okay, focused on it. Boom, boom. Right. Related rates are expressions, functions, formulas, with variables like x, y, z, r in them. But all these are functions of time. And so when we do related rates, we are typically trying to find derivatives with respect to time. Okay, let's give you an example. Suppose A is pi r squared, which it is. And suppose that A is representing a circle, but it's not a single fixed circle. It's a circle whose radius is changing with time, and its radius is increasing at the rate of 5 meters per second. Okay, can you imagine that? So that would be like the oil slick cylinder, right? A circle getting bigger and bigger and bigger through time. We would like to be able, right, to find the rate of change of the area with respect to time. And we'd like to know that at, oh, I don't know, t equals 5, or it's the same number, t equals 6, so about that. So this is how you do it. If you want to find the derivative of this variable with respect to time, but this variable is given in terms of this case r squared, the formula is differentiate a with respect to r times differentiate r with respect to t. Now, you notice I'm using Leibniz notation. You really have to with these questions. It works well with it. I know these are not fractions, and don't ever tell a professor I said they were fractions, because they're not really fractions, right? But they have a fraction-like look to them. How about that, right? Do you notice that these cancel out, sort of? So does this formula kind of make sense? In fact, it's really a version of the chain rule, if you really think about it. So you differentiate this with respect to r, and then dr by dt, was a fixed number. And so the answer would be 10 pi r. So if the question only asked find dA by dt, do you see that your answer would just be 10 pi r? That would be the end of the question. Now, if you wanted to find dA by dt, right, and you wanted to evaluate it at say t equals 6. To be able to do that, don't I need to know what r is at the 6-second mark? Great. I need to know what the value of r would be at the 6-second mark. Now, since dr by dt is 5 meters per second, at the 6-second mark, wouldn't it have been 5 lots of 6 then, right? 30. So I would be able to say it's 2 pi times 30, and the answer would be 60 pi. Typically, the variable, or variables are always going to have a value that's a fixed number, right? So dr by dt will be 2 or 4 or 49 or whatever, right? And so if it's a fixed value, every second it will travel 5 meters. So in 6 seconds, won't it travel 30 meters? So you're comfortable where that 30 came from. Right? If it was 10 seconds, wouldn't it be 50? Right? 10 seconds times 5. So far, so good. So suppose we have a sphere and the rate at which the radius is increasing is 4 feet per second. So I guess I'm essentially modeling an explosion. Can you imagine a ball going boom, right? And it's like in the air, right? So it would probably expand in all directions equally. So it would expand like a big ball, right? Big ball of flame, right? Big boom. And we would like to know then what the rate of change with respect to time of the volume is. And so that would be differentiate the volume with respect to its variable, r, times dr by dt. And if you differentiate this, it's multiply by the power and reduce it by 1. And dr by dt is 4. And so this would be 16 pi radius squared. And that would be the answer. Have you noticed that you don't turn that into a decimal? 16 pi is a much better answer than whatever horrible decimal 16 times 3.1412 is, right? So leave it alone, and that's good. Now, suppose they gave you, that was part A, and suppose part B said, what is the rate of change of the volume when t is equal to, say, 2 seconds, right? So 2 seconds after the explosion, if you took a snapshot of that big cloud of explosion, what would the thing look like, right? What would be the increase in the volume? How's it getting bigger? Well, dv by dt at t equals 2 second mark is going to be 16 pi times the radius squared. Well, since the radius is going at 4 feet per second, would you agree in 2 seconds that would be 8? 4 times 2 gets me 8. And then I can just multiply those together. And we get 16 times 8. And that gets me 128 pi. And I guess this is a volume thing, so it'd be cubic feet per second. So you can imagine that ball is going to get in the next second, what's that, about another 370 cubic feet bigger, right? So it's boom, 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 right, getting bigger and bigger. Now you can also do that same question, but from a different perspective. So we're going to, and we'll keep this guy exactly the same. But we're going to ask you to find the rate of change of the volume with respect to t when the radius is 12 feet. Which isn't that just a disguised way of saying in 3 seconds? We already know what dv by dt is. It's 16 pi r squared. And if you want to evaluate that when r is 12, it's just 16 times pi times 12 squared. And that's going to be 144 times 16, and that's going to be a huge number. And the units would be cubic feet per second. How are we doing with these questions? Is a formula in the usual sense, but where one of the variables, if there's only one, changes with time. Are you comfortable we can find these types of derivatives using the method we've shown you? Here's another version of that same thing. The surface area of a sphere happens to be that guy. And the rate of change of r with time is going to be 3 centimeters per second. And we are being asked to find, whoops, the rate of change of the surface area is 3 squared centimeters per second. So I'm going to tell you that, and I'm going to ask you to find dr by dt when r is 5 seconds. So can you imagine you've got a sphere, right? And this is the surface area of it. And this sphere, the outer surface, so it's growing, but it's growing at the rate of an extra 3 square centimeters per second, right? So it's just very slowly getting bigger. And we want to find what is the rate of change of the radius at the point when the radius is, get the units right, 3 millimeters. So you start, as you do with every one of the questions, with the function that you have, and then you're going to find this guy, and that's going to be ds by dr times dr by dt. And so ds by dt is going to be 8 pi r times dr by dt. So far, so good. Now, normally, you know what that guy is. You know, it's 5 or 10, and you just multiply that and you're done. But in this question, you're told this guy, right? And you're told he's 3. So how do I find dr by dt? Three is equal to 8 pi r times this guy. How do I find this guy?
Could you divide by 8 pi r?
Yeah, you just solve, just like you would do any equation. In this case, divide both sides, and there is your answer to that guy, right? Now, in this particular one, we wanted to know the answer when r is 5. So dr by dt is 3 over 8 pi r. Dr by dt then, when r is 5, becomes 8 over 3 over 8.5, and that's 3 over 40 pi. And we don't really care how ugly it is, we just leave it alone, and your answer is a very small amount. Would you agree? It's a tiny number, but that makes sense because it's growing very slowly. None of the numbers I've done so far have been negative, but is it possible to have negative in these stories? Yeah, couldn't you just get a sphere that's shrinking, right? So if an answer comes out as negative something, it just means whatever it is you're looking at is getting smaller with time rather than bigger. Any questions so far? We're good? Looking at happy faces, or at least non-scared faces. Question 2. Each side of a square is increasing at the rate of 8 centimeters per second. Okay, so here's a square. And you've just told me that the rate of change of that guy is 8 in the units of centimeters per second. And then they ask, at what rate is the area? So the area of a square is that. So when they're asking what rate, they're asking me to find the derivative of A with respect to t. So they don't tell you find dA by dt, they phrase it by at what rate is the area of the square increasing, right? So they're asking me that, and they're asking me to find that when the area is 81 centimeters squared. We'll worry about that bit after we've figured this all out. So we'll start with our formula and we'll differentiate it with respect to t. So it's going to be that guy is going to be dA by dx times dx by dt. So far so good. Now if you differentiate this with respect to x, you get 2x, and this guy is a fixed number, 8. So the answer that we're going to get for the first part is that the rate at which the area is changing is 16 times x. Now this fella wants us to find one specific value for that. They want to find the value of this when the area is 81. Now, wouldn't it be nicer if they said when x was 10? Right, that would have been nice, but they didn't. So if I tell you that the area is 81 and the area is x squared, so x squared is 81, are you comfortable that that was just a disguised way to tell me x was 9? And so I can now find the answer to what the rate of change of area with respect to time is at x equals 9. And the answer is 16 times 9, which on my calculator is 144. The units are square centimeters per second, if you're interested in units. We cool? This is a version a little bit trickier. The length of a rectangle is increasing. Oh, I better draw it. I always find it helpful to draw. The length of a rectangle, so I'll call L the length, is increasing at the rate of 9 centimeters per second. And its width is increasing, so I might as well call that variable W. And its width is increasing at the rate of 8 centimeters per second. And then it goes and it says, when the length is 15 and the width is 13, find the rate of change of the area with time. So we want to find how the area of this rectangle is with respect to time. And the length is increasing at once and the width is different. So can you imagine this was an animation? Wouldn't it be a rectangle, but as you watch the movie, wouldn't the rectangle get bigger? But it would get distorted. Wouldn't it be getting bigger lengthwise than it was widthwise, right? It's getting bigger more this way than it is that way, right? So it's not a same shaped rectangle getting bigger, it's getting distorted. Well, we know the formula for the area of a rectangle. You could its length times width. So technically there are two variables here, L and W. So we are now going to have to think of L and W as functions of time. So when I think of it that way, as area is a function of time, if I want to find the rate of change of area with time, I am going to have to call this F and this G, and we really have a product rule. Does that make sense? So the rules of this game are we are differentiating, but remember what we're differentiating with: time. Okay. So if you differentiate this guy with respect to time, you will get dl by dt, and you leave that guy alone. Plus, you leave the first one alone and you differentiate that guy with respect to time, you get that, and this will give me the derivative of area with respect to time. Does that make sense, what we've done there? Now, we should be able to, with the help of these snapshots, convert these into numbers and get the answer. So what do I know? Well, dl by dt is a fixed number, it's 9. The width in this was at 13 when that happened. The length is 15, and the rate at which the width is changing is 8. So we have 9 times 13 plus 15 times 8, and the answer is 237. It's an area, so it's square centimeters per second. Are you comfortable with that question, how we approached it? Question 6. A cylindrical tank with a radius of 7. So I like visual pictures. So here's my cylindrical tank, and its radius is 7, tells me that its radius isn't changing. Think of it as a big empty tank, right? Radius is 7. What we know about this tank, right? Well, it's been filled with water. So I'm going to have a variable. And I'm going to call that variable h to represent the height of the water. And what we told as I read on through the story, it's been filled with water at the rate of 4 cubic meters per minute. So you've just told me that the rate at which the water is going in is 4 cubic meters per second, okay? And you're being asked to find the rate at which the height of the water is increasing. So we need to have a formula, and that formula needs to contain this height. So if you imagine this as being a little baby rectangle, isn't the formula for a cylinder pi r squared h? Would you agree? Pi r squared h. Except this is not just any old cylinder, isn't it a cylinder whose radius is 7? So that's r squared becomes 7 squared, and so we now have 49 pi h. Are we comfortable about how I generated the formula for the water, volume of water? Right? It's 49, right, up 7 squared pi h. Now, differentiate this guy with respect to t, then it's dv by dh times dh by dt. Since there's only one variable, can't I do that? There's only an h. So dv by dt. If you differentiate 49 pi h with respect to h, don't you just get 49 pi? Agreed? Like 4x gets you 4. Followed by dh by dt. Now, we are being asked to find this fella. Right? And, oh, we know that that guy's 4. So that means I can put 4 here. And now I have this relationship. Isn't this very similar circumstance to an earlier question? And the answer is going to be the same basic way to do it. What should I do to find dh by dt?
Divide by 49 pi.
And it's ugly and it's correct. There's nothing I can do in this question, at least, to make that pretty.
I guess I'm confused on why the derivative of, I guess, volume is 49 pi.
Okay, so are you happy about the formula for the volume being 49 pi h?
Yes.
Okay, so if I went and said to you, V was 5h, and I asked you to find dV by dh, would you say 5? You wouldn't have a problem with that.
Yes.
So if I said V was 5 pi h, and I asked you to find this guy, you wouldn't be surprised that it was 5 pi.
Oh, okay.
And the 49 pi is just an ugly number, right? Just like 5. It really is just an ugly number. But it's a distracting ugly number, right? Because it makes you think something else is going on. So that's basically 5h. And when you differentiate 5h, then you just get 5. Okay, it's 49 pi h, but when you differentiate it, you just get 49 pi.
Okay, thank you.
You're welcome. Well, for the next question, suppose we have no story attached to it, but instead they give me an equation involving x's and y's. In this case, 4x squared plus 16y squared equals 100. And we are on x and y, like all these questions are functions of time. Now, let's suppose I give you more information. I tell you that the rate of change of y is a quarter. I tell you that the rate of change of x with respect to time is, oh, I don't, actually. I'm asking you to find that guy. And I'm also telling you that x is 3, and finally, y is 2. So here is the starting equation. I'm telling you the rate of change of y. I'm telling you the snapshot is when x is 3 and y is 2. And I'm asking you to find this guy. So I'll start with my expression, I guess you'd call it, or formula. And now I'm going to differentiate everybody here. But I'm going to differentiate them with respect to time. So ignore everything else. If you differentiated this guy, wouldn't the answer be differentiate it with respect to x and then finish with dx by dt? In other words, this guy gets you 8x times dx by dt. Isn't that very like a general? Right? 4x squared gets you 8x, that's the derivative bit, times dx by dt. In that same vein then, what would 16y squared get you if you differentiated it with respect to time?
32y times the derivative of y over dt.
Yeah. essentially, isn't this implicit or, well, no, I'm not calling implicit. I think chain rule's a better analogy. Isn't this very much like a chain rule? Now, if you differentiate any number with respect to any variable, isn't a number always going to get you 0? It doesn't matter what you differentiate it with respect to. Now, in this puzzle, we should know everything except one guy, which is dx by dt. So let's see what we have. 8 times 3, the unknown dx by dt, plus 32 times 2 times 1/4. Yeah, I tidied it up a little bit. That's 24 dx by dt. Oh, that's going to get me 16. Now, we're being asked to find this guy. Essentially, I'm going to solve an equation, right? I'm going to solve for that guy there, right? The guy I'm covering up. So as long as you do it to both sides, it's okay rule. So I am going to start by subtracting 16 from both sides. That seem reasonable? Subtract 16. And I am going to divide both sides by 24. And then I'm going to say I'm 99% right, but I want to be 100% right. So what's the only thing I haven't done that will make this 100% right?
You simplify it to 2/3, or negative 2/3.
I don't think I've missed that in any of the other questions, but can you pretend that this one down here was 48 pi, just for argument's sake, right? 4/48 pi, wouldn't you simplify that down into 1/12 pi? Right. So you're always expected to simplify a fraction. It just happens to be that none of the questions I think I did today, none at least I can recollect, I could simplify it, right? The answer I got was the end. But not always, right? So don't get into the habit of saying, oh, you just divide and that's it. You know, have a quick look. You might be able to do a little bit more. Are we good with that one? Okay, let's go crazy then. How about x squared plus 2y squared take away 3z squared equals 100. And we are interested in what is happening. I may change that number in a minute. At 2, y is 3, z is 5. Now, that number I'll have to change just to make the question correct. 4 plus 12, that's good. Take away 50. Yeah. It doesn't do anything to the problem, right? It just makes it legal, right? So suppose I have a relationship between 3 variables and it ends up being this number. And the snapshot is that when x is 2, y is 3, and z is -5. And I'm also telling you that dx by dt is 5, and that dy by dt is 3, and I'm asking you to find out what that guy is based on all of that, right? So that's the puzzle. Now, if you can do it with 2 variables, it's not that difficult. Would you agree to extend it to 3, 4, or 44? So I'll start with our original expression. And the reason why I wasn't bothered about that isn't that going to be 0 in a minute anyway. So it's not really going to change much. Differentiate then x squared, you get 2x dx by dt. If you differentiate 2y squared, you get 4y dy by dt. And if you differentiate this guy, you get -9 z squared dz by dt. And differentiate that guy, You get 0. Are you all comfortable with that line? Right. We've just done related rates, right? So, snapshot. X is 2, dx by dt is 5. That's that. Y is 3. dy by dt is also 3. Take away 9 times z squared dz by dt, and the whole thing's 0, right? So far, so good. Now, that gets me 20. That gets me 36. That gets me far too much. That gets me negative 220. Negative 225 dz by dt equals 0. That's 56, which I'll subtract from both sides. And dz by dt is that guy divided by that. Since they're both negative, it means the final answer is positive. And I'm pretty sure I can't simplify that fraction. So that's finished. But if you don't know, or you're just not sure, you can do a double check. 56 divided by 225. Hit the math button and choose number 1 fraction. And do you notice it just returned back to the original? That means you can't simplify it. Because, you know, I've been caught out. You know, sometimes 17 works for both of them, and you never even thought of that as a common factor, right? So you can do that. It's pretty quick. Now, same question, same information almost. X squared plus 2y squared, take away 3 squared is equal to 200, negative 234. I told you that was 5. I'm not changing that. I'm going to tell you that that is 3. Not going to change that. You know you need to know Z to answer this question. I told you it was 5. I might not tell you, or the question might not tell you it's 5, but you still need to know that it's 5. How do you solve for Z? Before you even go there, you need to know Z. How do you find Z?
Evaluate the function for x, y, and then solve for z.
Okay. So here is the original, untouched. Put 2 in there, so that's 2 squared. Put 3 in there, that's 2 times 3 squared. Take away 3z cubed equals this guy. Now, fingers crossed that that is why I said it is 5, right? So this is 4, this is 36, this is take away that guy, and it's negative 234. This guy is 40. If you take 40 away from that, you get negative 200 and...
Professor,
Yes.
I think it's 18 instead of 36.
Oh, thank you, because that was not going to work. I'm glad you've caught that. So that's 22, so that's 200 and... What is that? 22, 56, 256. So negative 256 over negative 3. That's not going to work either.
Cubed.
Cubed. Still not going to work. I want that to be a nice number. Has to be 125. Anyway, if I had done the thing correctly, wouldn't I just find the cube root of that guy, and that would have been Z? So, can you pretend that that was true? Otherwise, we have to redo the entire question. But that's how you would find Z. Oh, good. It gives me a chance to redeem myself. No, it doesn't. It's too late. Last name. Bye-bye. And tomorrow, I'm going to do another one of these questions, but this time I'll use a homework question, which is always safer because the numbers work out. But too late now. Okay, bye-bye, and I'll hang about for any questions. And remember your last name.